Dr. El-Gohary, thank you so much for joining us this afternoon. I'd like you to open up by sharing a little bit with our listeners about who you are and what you do and how you got involved in space.
Thank you so much for having me. My name is Tariq El-Gohary. I am an assistant professor at the Mechanical and Aerospace Engineering Department at UCF. I got my bachelor. I'm originally from Egypt, from Cairo. I got my bachelor's in mechanical engineering. And when I was doing my bachelor's, I got very interested in aerospace applications. My university back home did not have an aerospace major, so I went with mechanical engineering. And afterwards, I worked a little bit in the industry and then started my graduate degree at Texas A&M. And yeah, afterwards, I became an assistant professor, and I am an assistant professor at UCF since then.
So tell us a little bit about how UCF is making its way kind of into the aerospace map. I mean, it's kind of risen pretty high over the last few years as far as aerospace is concerned. Am I right?
It actually did, yes. There is a lot of focus from everyone, especially in the College of Engineering and Computer Science and the College of Science as well, on space applications. UCF has been involved in a significant number of proposals and grants and projects that and collaborations with Kennedy Space Center historically and until now. A lot of our MEE faculty and physics also faculty are having space applications, and also to mention the Florida Space Institute, which is also connected to us, and the Florida Space Grant Consortium, which is also connected to UCF. So there is a lot of space activities going on at UCF, and I'm very happy to be part of that.
Right, thank you. First question is, who do you see as the biggest companies that have a presence on UCF campus? Because my experience is companies look at university kids as the labor pool, right? They're always looking for future employees, and maybe they intern first and then get full-time jobs. From your vantage point, which companies do you see have the strongest presence on UCF within the aero world?
Based on the classes that I have taught, a lot of the students who are, for example, doing a part-time master's or a part-time PhD in our program are already employed in some of those companies.
Oh.
Obviously, one of the major companies that hire our students is Lockheed Martin. In general, all aerospace defense contractors have been hiring UCF students for quite some time now. UCF has been ranked #1 in that category for the past few years, I believe. So a lot of the aerospace defense contractors have been hiring UCF students, such as Lockheed Martin, Northrop Grumman, and so on. And from the government side, I had students, or have actually a master's student from Eglin, from the Air Force, and some other students from Kennedy Space Center. So that is also some of our students are already employed by those government institutions. More recently, I had a student in my class who was hired by the Aerospace Corporation in California. So now we're going even a little bit beyond Florida,
Right.
and our aerospace graduates are going to, they're having more exposure in places that we're not hiring UCF students in the past, maybe 10 years or so ago.
Right. Well, the Aerospace Corporation, I believe, is an FFRDC, federally funded research development corporation. So that's like MITRE or Oak Ridge. Those are very prestigious organizations.
Exactly.
That's actually a really good feather in your cap.
Yes.
I'd like to pivot back just a minute. I would like to know, when you were in grad school, what was your most enjoyable classes? The focus, the effort, the basis of your thesis, and then how did that translate to your UCF lab? And we'd like to know about the work being done in your UCF lab.
Sure. So while in grad school, we had 3 disciplines in the aerospace department. So Texas A&M had a dedicated aerospace department, not like a mechanical and aerospace like we have here at UCF. So within that department, we had the 3 main categories: dynamics and controls, and the fluid or aerodynamics, and then the structural or continuum mechanics. So the one that really caught my attention and I was very enthusiastic about was the dynamics and controls group. And that's what I ended up doing in aerospace. Now, when I did my PhD, I became more and more interested in astrodynamics, which is related to space motion and satellite space flight mechanics and so on. So that's where I mainly focused my PhD on. And when I started my tenure here at UCF, I started focusing on that, more on the astrodynamics. And what I did here is that I established the Astrodynamics Space and Robotics Lab, which is the name of my lab. And we're basically working on 3 areas related to space research. The first one is related to astrodynamics or space, mostly space situational awareness applications. The other area, which is related to entry, descent, and landing, which has a more control aspect to it. And we have a couple of collaborations on that area. In the space related activities, we're collaborating with our physics department on understanding the motion of electrified or charged lunar dust on the lunar surface. So that's a project that I'm using my dynamics background to explore. And finally, we have built a couple of robots that can basically do space motion emulation in the lab so that we can sort of emulate or simulate some of the missions or the sensing missions that we are looking at in the theoretical research using robotics. So it has also been quite a success. Mostly undergraduate students have been working on the robotics aspect of my research, and they have published in SciTech and AIAA student conferences. They've been doing very well.
That's
Yeah.
That's fantastic. If I were to give you a piece of graph paper, a TI-84 calculator, mechanical pencil, could you start from a blank page and show us every step of the way of that Falcon 9 first stage return?
I wish.
Can we fit that on one piece of paper?
I wish I'm that good.
Well, maybe you could help us, the lay person, understand it better. They rely on a lot of redundancy and a lot of GPS data, do they not? To
Yes,
a precise landing point.
Yeah, so if you looked at the regular entry, descent, and landing problem that have been explored since the early stages of the space era. So we're talking Apollo and you know, and then I would say that the cornerstone of it was the Apollo reentry. And based on the Apollo reentry, we had MSL and pretty much all the landing missions that came to other landing missions, not necessarily reentry to Earth, use the Apollo algorithm as basis for that.
Doc, what is MSL?
I'm sorry?
I thought you used an acronym MSL.
Uh-huh.
What does that mean?
Oh, this is sorry, Mars Space Laboratory.
Okay, Mars Space Lab. Okay.
Yeah. Okay, so so essentially that's the cornerstone of all of that was related to the Apollo era algorithms. And one of the things that we've been looking at in future lunar missions and future Mars missions is how to gain the knowledge of those of the previously developed Apollo algorithms and build on that forward. Now, related to the controlled descent that the Falcon 9 does, I guess you can teach or you can model it. The simplest thing is an inverted pendulum problem. Okay, so if you think of, you know, that you have a pencil or a rod and you're trying to stabilize it in your hand, and you're basically, that's sort of the basic problem that you can be looking at. And obviously it is a lot more complex than that because you have atmospheric effects and you have the initial velocities and also you have to account for a lot of the other factors that affect entry and landing or re-entry, like the heat and so on, to land it safely. But you can model it as an inverted pendulum problem, stabilizing a rod in your hand. And basically,
Wow.
instead of you moving the base to make the rod or the stick straight, you're using thrusters and
Right.
all kinds of controls to essentially come up with this re-entry trajectory. Now, the trajectory itself is a function of a lot of things. It's a function of how much control authority you have to stabilize. It's a function of all the heat problems that are basically that could affect. Also, it's a function of where did you start your entry problem from, and where do you want to land as well.
Okay.
So you basically start constructing the problem from there.
Quick follow-up on that. Is it how much more difficult if all the weight on that first stage is up at the top on reentry versus the bottom? Because I think of a lawn dart or something that's, it's heavy on the end that's coming to the ground first.
Mhm.
How much more stability issues would you have if the weight center of mass was much higher up towards the other end of the rocket?
Yeah, obviously it makes a difference, because the all the equations or the developments you're gonna do will be to stabilize that center of mass. And as you change that, and it does change, the center of mass for these problems is not a constant. It's not in some, like there's fuel and you're burning fuel, and basically the weight as your burn fuel is changing and the mass distribution changes, and the center of mass location also changes. So that's also
Right.
another aspect of it. But yeah, obviously the closer you have it to where you want it to be stable, the better.
Fantastic.
Yeah.
I'm going to go back to another item that you mentioned was part of your research study, and that is space situational awareness. So kind of let our listeners and me know what that is. I know general situational awareness. What do we have to be concerned about with that in space?
So the space situational awareness, and now the Space Force is using another term called space domain awareness, is essentially related to a lot of things. You can define it as following. You can define SSA or SDA. Those are the acronyms for both. Related, you can say that it's basically the process of acquiring measurements in space, acquiring measurements of either active satellites, inactive satellites, debris, which is coming from breakups of satellites, and so on. Essentially acquiring those measurements. So that's one area of it. And then the other part of it is processing those measurements. Okay, so processing those measurements lead to so many different things related to predictions, correlations, catalog maintenance, and probability of collisions, for example. So measurement acquirements, there is the Space Surveillance Network, which is also managed by the Air Force / Space Force. And it's a bunch of ground observers, telescopes that look at the sky and quantify where various space objects are. And those measurements turn into data, and the data is used or processed to understand where those things would be in the future. And if, let's say, Station A picked up an image and Station B later on picked up another image, which objects in image A are the same, or are the same objects in image B, which is the correlation problem. Now, currently, I believe there's about the database is about 25,000 objects that we are keeping track of. This number might have changed. However, that's sort of what I think it's around that number. And those include active and inactive debris, like first stage kind of stuff. And estimates are that we have about in the 500,000 objects between 1 centimeters and 10 centimeters in diameter. So 10 centimeters about a baseball kind of size. So we're keeping track of about 25 to 30K above 10 centimeters.
So Kevin, is that what they were doing when they were trying to track the satellite?
I believe you're talking about like the space catalog, right?
Yeah,
the
exactly.
18th. I love that. I love just searching that. You can see objects that were launched in the late 50s and early 60s.
Right. So that's the
And you
kind
can basically see, get the, get the coordinate, get the orbital elements and be able to.
So this is Celeste track you're talking about, right?
Yes.
Yeah.
Yes.
So you get the TLEs, the two-line elements, and yeah.
Love that. Love the two-line elements.
Yeah.
Well, let's go a little bit now to the Lunar Dust project, right? Which is one that I know, when I first started working with Kevin, that first group of kids started to come up with the idea of a lunar rover. And I think you've met my son, Caden. So that's kind of how he ended up at UCF.
Yeah, that's
So
great. Yeah.
thanks, by the way. Like, he is loving it. And
he just sent me a message earlier this afternoon about his progress, and I'm really happy to have it.
I've been looking at his notes so far above me, but I want to go to the lunar dust thing just because, I feel like that's something that I might understand myself just a little bit more. So tell our listeners, what are the problems with lunar dust anyway? Why do we need to mitigate it in the first place?
All right. So since the Apollo, the lunar dust has not been looked at very favorably. There are quotes from the astronaut that it goes everywhere. Cleaning is quite hard. And it wasn't a very pleasant experience for anyone involved. And those are based on the accounts of the astronauts during that time. Now, so this problem has been out there since then, and NASA launched a mission to basically understand a little bit about lunar dust and whether the electrostatic effects are capable, or the lunar charging is capable of pushing dust into orbit. And they did send a probe also around, I want to say, late 60s, 70s, in that range, to measure that effect. So it's been a problem that has been on the minds of everyone related to lunar exploration for quite some time now. But I guess the problem is going to be much more challenging as we are planning to put more missions on the moon and on the lunar surface. So as you know, there is the Gateway. NASA is launching the Gateway, and then the Artemis program, and there will be more astronauts and more frequent missions. There's also the lunar habitats, which is planned to have people and equipment continuously on the lunar. So all of these things made the lunar dust problem, quite pressing, because number one, the hypotheses that exist that the lunar dust gets charged and lofted and move around, these are mostly theoretical. The other area is that we don't have models that really can predict well where all these, like let's say lunar dust gets lofted due to a rover, for example, on the lunar surface, and it gets pushed one direction or the other. We don't have really good predictions on where all of that dust would land. And it has been observed that it doesn't really follow what you throw a stone or a piece of anything and it goes like in a projectile motion. It doesn't really do that. It can hang up in the air for longer than expected, and it can actually go further than what is expected. And this is very important to understand, because if you're going to have frequent missions, landing and launching activities near habitats and equipment and solar panels that sustain these habitats, then you have to understand, number one, where is it going to land, where all of that dust is going to go, so that you can, design your equipment and place your equipment optimally. And also, when it accumulates, it can block, for example, sunlight on solar panels. It can overload structures and so on and so forth. So the other side of the problem is how, if we understand how it moves and we understand how it gets charged and discharged, how we can actually push it off and clean it off the surfaces that it could land on. I'm more concerned with the first part, understanding how it moves from a science/physics perspective, but there is a lot of activity also going on at NASA and different centers, especially KSC, to basically do dust mitigation and push the lunar dust from various surfaces.
Yeah, no, and I think too, like, I can't even imagine how you'd begin to test on that. I know that there's regolith, right, which is something that's kind of like, I guess it, but we can't use you wouldn't be able to test these kinds of things with the dust in places like, say, the desert, right? Because not even close. So how is regolith then, why is that the best method to use versus say something that we might think of otherwise.
So you mean the simulated regolith, right?
Right, yes, the
Yeah,
one that I think that
Similar.
UCF actually has a
Excellent.
laboratory.
So, yeah,
excellent,
so
excellent,
so it gets created based on the components of the actual lunar dust. So they have the same properties in terms
Got
of
it.
the various physical properties of lunar dust. So that's why it is unique. And the composition of lunar dust is obviously not similar to our,
Right, right. So it wouldn't even make sense to even try to figure out anything because the components are completely different.
Were the in the creation of the like a lunar regolith sort of simulant, did they go as far as trying to make the particles the same shape? Because I know regolith is sort of like a jagged,
Yeah, I believe I'm not very familiar with how the intricacies of how they make it at Exolith, which is also affiliated with UCF, as you probably know.
Yeah.
But I believe that yes, they do produce irregular shaped particles.
Right.
Yeah.
That's cool. From your vantage point, we look up at the moon, we see the really bright white areas, we see the darker areas, the Maria or the highlands. Do you believe behaviorally these different regions, the suspended dust or the ionized dust will behave much differently or very similarly, or you don't know, or somewhere in between?
Well, I think it will be a function of the composition of the lunar dust, and it does vary from location to location. So that is definitely an aspect of it, is that when you have, I'm sorry, I'm just gonna silent this. So when you have that aspect of the location, it changes the composition of the dust, and that in turn changes its internal properties and the way it gets charged or lofted and moved around. Because again, the hypothesis is still in electrostatics and charging and discharging and contact charging as well. So that all is affected by the material properties of the dust. And from location, it does vary. And there are also samples that cover some of those areas based on the explorations that happen through the Apollo era.
So if you figured out how it was moving, which is what you said, that like what is making it go in which particular direction, then that could also be applied to NASA's other issue about, whether it's clogging those things and the other issues that come around, because you're looking to move it. What would then propel it away? Is that correct? You could kind of connect.
Yeah, because we're using electrostatics, or we're examining electrostatics to see if it actually moves, how far it can push. And you can look at it that the inverse problem. So if I want to push it this far, how much charge I need. So you can also look at it from that perspective. Yes.
Yes, we need some sort of electrical lunar dust, leaf blower to keep our solar panels working efficiently. That I feel like having power on the moon is important, right? No power, not much else.
Well, I think that was one of the big issues with the kids rover idea that they originally.
Oh no, that was our
with,
mission. Right? Our mission statement was to evaluate electric or magnetic fields or both on
no, but
panels.
I think their issue with the dust was the motility, like how the rover was going to go. They had these kind of tractor kind of wheels, and the dust was going to
paddles, wheels, treads. I think those are three big ways they look at trying to move that. I think there's a lot of future. Fantastic. So I want to just pivot again back towards UCF. So you've got undergrads that are quickly being hired by NASA companies on Space Coast companies and other places. And then you have full-time aerospace employees that are coming back to UCF on a part-time basis for masters and doctorates. Does that sound?
Yeah.
Did I hear that correctly?
Yes.
So that's great. Would you say
you have also full-time PhDs as well?
Right.
Yeah.
Would you say you teach more undergrads or grad students?
I taught more grad courses until now. I taught more grad courses than undergrads.
Excellent. How long have you been at UCF?
6 years now.
Wow. Are you on track to be a full professor soon?
Well, no, it takes longer than that.
I was at UCF I graduated in 1998, and I was not in the aerospace or engineering field, of course, at all, but it's changed so much, and it's really great to see how well recognized it's becoming.
Right.
For the sake of time, we always ask the same last question, kind of like our listeners are thinking about aero engineering, they're thinking about places to go. What advice do you have for our students or even our parents who are listening about how a student who might be as young as middle school really be preparing if this is their path?
Yes, I think having a passion for it is important, and this will make a lot of the hard work required very enjoyable. So obviously, a good foundation in math and science, and you can go either way. You can be more focused on physics and physical phenomenon in space, or you could be focusing more on the engineering. And for both, you're going to need a good math and scientific foundation in middle and high school. From then on is basically, you know, going through the proper training of joining a school that has a good program. And I think, yeah, something like UCF will university like UCF with how many students getting hired by all the space companies is a very good candidate for students who have a passion for something like that. And it's not just, you know, it could be a lot of other things, not just motion in space or lunar dust or robotics. It could be structures, very much needed. It could be propulsion. It could be aerodynamics, which is also quite important for landing on bodies with atmosphere. So all of these things are quite important. So yeah, and all have a good people or students should have a good foundation in math and science and a passion to go through the education and training. But other than that, it's a piece of cake.
I don't know. Caden was showing me some of those notes, and then he's like, "Wow, he's like, he's definitely he's just taking it on." But woo, added. So anyway.
If you don't love that material before you get into it, it's going to be miserable. You'll be a miserable child.
I think that applies to anything. It doesn't.
That's true.
Yes.
Applies
Very
to
Yeah.
people can, you know, apply themselves and you know, it's never for a very, very lucky few number of people, it's just, you know, a walk in the park. But for all the majority of mortals like us, it requires hard work.
and be willing just to not give up and just take a little longer with it. I think.
Yeah, exactly. So, you know, it requires hard work, it requires determination and self-motivation, you know, being self-propelled. And yeah, a lot of the times you will come across things that are very hard to understand and are very complex and feels like way above your head, but that doesn't mean that you're not cut out for it. You just need to work a little bit harder on it, and it will all unravel and, you know, make itself reveal itself to you at one point. Yeah. So yeah, that's it.
Dr. Tariq Elgohary, I want to thank you for taking the time to meet with us today. We had a blast, and we are so looking forward to the work and the students' work that's coming out of your lab. So thank you for being with us today.
Thank you so much for having me.